Welcome to Geology 108, Matter. We will discuss some important aspects of matter that are used to understand how compounds, minerals, and rocks form. Matter is made of atoms. An atom is the smallest individual particle that retains the distinctive properties of a given chemical element. Atoms consist of subatomic particles, protons, neutrons, and electrons. A simple model of the atom has a central nucleus composed of protons, which have positive electrical charges, and neutrons, which have no electrical charge. A cloud of negatively charged electrons surround the nucleus, the number of electrons equaling the number of protons, thus balancing the positive charge of the protons for an electrically neutral atom. Protons and neutrons have a mass number of 1. The mass of an electron is less than 1,000th of that of a proton or neutron, meaning that most of the mass of an atom is in the nucleus. Isotopes are atoms with the same atomic number but different mass numbers. In other words, different isotopes of the same chemical elements have the same number of protons and electrons, but different number of neutrons. Different isotopes of the same element share the same chemical properties, but have different mass density. Some isotopes are radioactive and can be used in radiometric dating. Matter is composed of elements which are atoms that have the specific number of protons in the nucleus. This number of protons is called the atomic number for the element. For example, an oxygen atom has 8 protons and an iron atom has 26 protons. An element cannot be broken down into a simpler form and still retain unique chemical and physical properties. Each element behaves in a unique manner in nature. The periodic table of the elements is a tabular arrangement of all known elements listed in number of their atomic number. The first arrangement of elements into a periodic table was done by Dmitry Mendeleev in 1869. In the periodic table, each element has a chemical symbol, name, atomic number, and an atomic mass. The chemical symbol is an abbreviation for the element, often derived from a Latin or Greek name for the substance. The atomic number is the number of protons in the nucleus. The atomic mass is the number of protons and neutrons in the nucleus, each with a mass number of 1. Since the mass of electrons is so much less than the protons and neutrons, the atomic mass is effectively the number of protons plus neutrons. The atomic mass of natural elements represents an average mass of the atoms comprising that substance in nature and is usually not a whole number. Elements exist in nature with atoms having different numbers of neutrons, affecting the mass of the element. The atomic mass number represents this average. Elements with the same chemical properties, that is, the same number of protons and electrons, but different number of neutrons, are called isotopes. There are usually several isotopes for a particular element. For example, 98.9% of carbon atoms have 6 protons and 6 neutrons. This most common isotope of carbon is called carbon-12. A few carbon atoms, carbon-13, have 6 protons and 7 neutrons. A trace amount of carbon atoms, carbon 14, has 6 protons and 8 neutrons. Among the 118 known elements, the heaviest are created in high-energy particle accelerators. They are unstable and decay rapidly. The heaviest naturally occurring element is uranium, atomic number 92. The 8 most abundant elements in Earth's continental crust form the most common rock-forming minerals. The elements oxygen, silicon, aluminum, magnesium, calcium, and iron are the most common in the rocky terrestrial planets and moons, making up 98% of their mass. Most substances on Earth are compounds containing multiple elements. Chemical bonding describes how these atoms attach with each other to form compounds, such as sodium and chlorine combining to form NaCl, common table salt. Compounds that are held together by chemical bonds are called molecules. The electrons around the atom's nucleus are located in shells representing different energy levels. The outermost shell is called the valence shell. Electrons in the valence shell are involved in chemical bonding. Atoms are more stable when their outermost shell is full. Therefore, atoms of most elements tend to gain or lose electrons, so the outermost or valence shell is full. The total number of electrons to fill the first, second, and third shells are 2, 10, and 18, respectively. Elements with these numbers of protons, like helium, neon, and argon, are called noble gas and are chemically inert. Other elements need to engage in chemical bonding to fill their electronic structure. Atoms like to combine to form chemical bonds by sharing or transferring electrons. Sharing of electrons occurs in covalent bonds. Transferring of electrons occurs in ionic bonds. In metals, a cluster of atomic nuclei float in a sea of electrons. Ionic bonding occurs when two atoms exchange one or more electrons. An atom is electrically neutral because the positive charge of the protons balances with the negative charge of the electrons. An atom that has excess positive or negative charge is called an ion. Ions have achieved full valence shell by lending or borrowing electrons from a different atom. When an atom gives away an electron, there is one more positive proton than negative electron, so the ion is positive and we call it a cation. Reciprocally, if an atom received an electron, there is one more electron than there is proton, so the ion is negative and we call it an anion. For example, one atom of sodium, Na+, and one atom of chlorine, Cl-, form an ionic bond to make the compound sodium chloride, NaCl. This is also known as the mineral halite or common table salt. In a solution, sodium gives away an electron that is borrowed by chlorine. Sodium becomes the cation Na+, and chlorine becomes the anion Cl-. Ionic bonds are usually formed between a metal and a non-metal. A covalent or electron sharing bond commonly occurs between non-metals. Covalent bonds share electrons to complete the valence shell of the atoms involved. For example, oxygen, atomic number 8, has 8 electrons, 2 in the inner shell and 6 in the valence shell. Gases like oxygen often form diatomic molecules by sharing valence electrons. In the case of oxygen, 2 atoms attach to each other and share 2 electrons to fill their valence shells to become the common oxygen molecule we breathe, O2. The subscript 2 in the chemical formula indicates the molecule contains 2 atoms of oxygen. Methane, CH4, is another covalently bonded gas. The carbon atom needs 4 electrons and each hydrogen needs 1. Each hydrogen shares its electron with the carbon to form a molecule as shown in the figure. Water, H2O, is a compound of hydrogen and oxygen in which 2 hydrogen atoms are covalently bonded with 1 oxygen, making the water molecule. Nitrogen, ammonia, carbon monoxide, and carbon dioxide molecules are all formed from covalent bonds. Metallic bonding occurs when lots of atoms have too many electrons. Metals abandon their electrons to form a giant soup of electrons floating around the cluster of atomic nuclei. Electrons are delocalized, so they are free to move around, forming excellent electric conductors. The atom nuclei become positively charged and attracted to the sea of electrons. Matter can be found most commonly on Earth's surface in 3 different states: gas, liquid, and solid. In a gas, particles can move past one another. With lots of space between particles, a gas is compressible and flows easily. In a fluid, particles can move or slide past one another, but there is little space between particles and a fluid is not easily compressible. However, a fluid can flow easily. Examples of geological fluids include water in the ocean and lava. In a solid, particles are locked into place with little space between particles. Hence, a solid does not flow easily. Another important state of matter is plasma, consisting of an ionized gaseous substance that is highly electrically conductive to the point that long-range electric and magnetic fields dominate the behavior. Plasma makes up our sun and all other stars and is the most common state of matter in the universe as a whole. Most minerals are compounds of more than one element. The common mineral calcite has the chemical formula CaCO3, indicating that the molecule consists of 1 calcium, 1 carbon, and 3 oxygen atoms. In calcite, 1 carbon and 3 oxygen atoms are held together by covalent bonds to form a molecular ion called carbonate, which has a negative charge. Calcium, as an ion, has a positive charge of +2. The 2 oppositely charged ions attract each other and combine to form the mineral calcite, CaCO3. The name of the mineral compound is calcium carbonate, or calcium is Ca2+, and carbonate refers to the molecular ion CO3 2-. The mineral olivine has the chemical formula MgFe2SiO4, in which one silicon and 4 oxygen atoms form the silicate tetrahedron SiO4 4-, which is an anion compound that bonds with 2 ions of either magnesium, Mg2+, or iron, Fe2+. The comma between iron and magnesium indicate the 2 elements can occupy the same location in the crystal structure and substitute for one another. Minerals form where atoms bond together in a crystalline arrangement. 3 main ways this occurs in nature are: 1, precipitation directly from an aqueous solution with a temperature change. 2, crystallization from a magma with a pressure or temperature change. And 3, biological precipitation by the action of live organisms. Solutions consist of ions or molecules known as solutes, dissolved in a medium or solvent. In nature, this solvent is usually water. Many minerals can be dissolved in water, such as halite or table salt, which has the composition sodium chloride, NaCl. The Na plus and Cl minus ions separate and disperse into the solution. Precipitation is the reverse process in which ions in solution come together to form solid minerals. Precipitation is dependent on the concentration of ions in solution and other factors such as temperature and pressure. The point at which a solvent cannot hold any more solute is called saturation. Precipitation can occur when the temperature of the solution falls, when the solute evaporates, or with changing chemical conditions in the solution. An example of precipitation in our homes is when water evaporates and leaves behind a rind of calcium carbonates in faucets, shower heads, and drinking glasses. In nature, changes in environmental conditions may cause the minerals dissolved in water to form bonds and grow into crystals or cement grains of sediments together. Stalactites, for example, these ones at Gartner's Gut Cave in New Zealand, form from the precipitation of calcium carbonate in groundwater. Another example, close to Los Angeles, is the Trona Pinnacles in the Mojave Desert of California. During ice ages of the last 3.5 million years, a recent period called the Pleistocene, massive runoffs spilled from the Sierra Nevada into a chain of inland seas. The system of interconnected lakes stretched from Mono Lake to Death Valley and Searles Lake. Deep beneath Searles Lake, calcium-rich groundwater and alkaline lake water combine to grow tufa formation. The tufa pinnacles formed underwater 10,000 to 100,000 years ago. Another example of precipitation occurs in the Great Salt Lake, Utah, where the concentration of sodium chloride and other salts is nearly 8 times greater than in the world's oceans. Streams carry salt ions into the lake from the surrounding mountains. With no other outlet, the water in the lake evaporates and the concentration of salt increases until saturation is reached and the minerals precipitate out as sediments. Similar salt deposits include halite and other precipitates and occur in other lakes such as Mono Lake in California and the Dead Sea in Israel. Heat is energy that causes atoms in substances to vibrate. Temperature is a measure of the intensity of vibration. If the vibrations are violent enough, chemical bonds are broken and the crystals melt, releasing the ions into the melt. Magma is molten rock with freely moving ions. When magma is emplaced at depth or extruded into the surface, then called lava, it starts to cool and mineral crystals can form, a process called crystallization. The minerals that make up igneous rocks crystallize at a range of different temperatures. A cooling magma can have some crystals within it and yet remain predominantly liquid. The sequence in which minerals crystallize from a magma is known as the Bowen reaction series. Of the common silicate minerals, olivine normally crystallizes first at temperatures between 1200 and 1300 degrees Celsius. As the temperature drops, the olivine crystals combine with some of the silica in the magma to form pyroxene. This process continues with olivine to pyroxene, pyroxene to amphibole, and amphibole to biotite. Many organisms build bones, shells, and body coverings by extracting ions from the water and precipitating minerals biologically. The most common mineral precipitated by organisms is calcite or calcium carbonate, CaCO3. Calcite is often precipitated by organisms as a polymorph called aragonite. Polymorphs are crystals with the same chemical formula but different crystal structures. Marine invertebrates, such as corals and clams, precipitate aragonite or calcite for their shells and structures. Upon death, their hard parts accumulate on the ocean floor as sediments and eventually may become the sedimentary rock limestone. Another example is the marine organisms called radiolarians, which are zooplankton that precipitate silica for their microscopic external shells. When the organisms die, the shells accumulate on the ocean floor and can form the sedimentary rock chert. Chert is typically composed of the petrified remains of siliceous ooze, the biogenic sediment that covers large areas of the deep ocean floor. Minerals are the building blocks of rocks and essential to understanding geology. Mineral properties are determined by their atomic bonds. Most minerals begin in a fluid and either crystallize out of cooling magma or precipitate as ions and molecules out of a saturated solution. The silicates minerals, based on the silicon-oxygen tetrahedron, are the largest group of minerals on Earth by number of varieties and relative quantity, making up a large portion of the crust and mantle. The crystal structure of silicates reflect the fact that silicon and oxygen are the top two of Earth's most abundant elements.